You've got the basic endpoint behavior. A linear function starts down in the third quadrant, ends in the first, or if it's a negative leading coefficient, it does this. A third degree function starts down here in the third quadrant, ends in the first, or vice versa if it's a negative. A fifth degree function, you still see the same thing. Your end behavior stays similar. Your second and your fourth degree, it either starts in the second, ends in the first for second degree, or if I have a negative leading coefficient, it starts in the third, ends in the fourth. You see that again with this. I know it's a little scrambled here because of everything, but that's generally it. That's our end behavior similarity. Right? That's something that I'll answer the question here. Also, which of these have to have an x-intercept? Which of these five groups have to have an x-intercept? The first, third, and fifth, because they all start below the x-axis and end above it, or if it has a negative leading coefficient, it starts above the end, the x-axis, and ends below it. These guys don't have to. In this case, we actually do have x-intercepts for everything. Oh, not this guy. This guy doesn't have an x-intercept, but the other ones do. But we can always draw a quadratic without an x-intercept. Just like down here, we drew a quartic without an x-intercept. It can have 0. You can also have, in our quadratics, we have examples of 1 x-intercept where it touches, or 2 x-intercepts where it crosses, and then the example I have up here of 0 x-intercepts. Down here with the quartic, we could have 0. We drew that. 1. We also have 1, or we drew 1 with 4 x-intercepts. Can you picture a quartic graph that has 3 x-intercepts? The quartic graph for me that would have 3 x-intercepts would be touching at one point. And then if it had 2 x-intercepts, it would not look something like that. So you could have 0 through 4 x-intercepts for a quartic. For a quintic, a fifth degree, you have to have 1. It starts down here and ends up here. If you don't need, but you could have 1, 2, 3, 4, or 5 x-intercepts. We've got ones with just, or 3 examples with 1 x-intercept and 1 example with 5 x-intercepts. But there are, again, there would be one with 4 x-intercepts. If I put this up above higher, it would be 3 and so forth. So I'll give you a minute to copy this down if you want. Actually, what I'll do is I'll put it back up here later on so you can copy it down. This is how I describe my end behaviors. So as I said, I'll put this back up later on for you to copy down, because I've kind of gone through the process of it. So how are the graphs and equations of linear, cubic, and quartic similar? They have the same end behavior. For the graphs, and they are odd degree functions. So linear first degree, cubic third, quintic fifth. We could talk about similar properties with 7th, 9th, 11th. We aren't going to, but we could. Okay, so again, same end behavior. Now, when I talk about end behavior, I'm talking about where the graph starts and ends. So which quadrant does it start? Which quadrant does it end? So in the case of quadratic and quartic, they both start in either 2 and end in 1 for a positive leading coefficient, or start in 3 and end in 4 for a negative leading coefficient. Takes a couple bumps. They could have more bumps in a quartic, but that's generally more turning points in a quartic, but that's generally what we deal with. And then they're all even numbered, even degree functions. I got to make sure that I always put that degree in there, because an even function is a different thing than an even degree function. This is basically our relationship between the degree. If it's odd, it starts in 3, ends in 1, or starts in 2, ends in 3, or ends in 4, I should say, which is basically what I'm doing here graphically. And even starts in 2, ends in 1, or starts in 3, ends in 4. Oh, I won't bother writing this one. What's the sign? If it's positive, that's one way. Positive odd starts down here, ends up here. Negative odd starts up here, ends down here. Positive even, positive odd. So basically, just with these guys, this is positive leading coefficient, this is negative. Positive and negative. And here's something that we always have to ask ourselves. What's the relationship between the constant term of that function and the and something on the graph? So what do I mean by constant term? If I give you an equation, what's the constant term? Constant term has no variable in it. Okay, so in an equation like this, constant term is 3. What part of the graph, or what feature of the graph corresponds to that 3? Yes? The y-intercept. So the constant term is the y-intercept. And that works for everything written in general form. Okay, not so much in factored form, but if I have anything written in general form, which is all of those ones that you saw on that sheet, were all in general form, then the y-intercept always is that constant term. The x-intercepts are harder to find. We have to do some factoring, which we spend a lot of this unit on. Because we should know how to factor second-degree functions, but you definitely don't know how to factor third-degree functions. Okay, so the relationship between the minimum and maximum number of x-intercepts and the degree. Maximum is the degree of the function. So if I say I have a 10th degree function, I could have up to 10 x-intercepts. Okay. The minimum depends upon if it's odd or even. The odd degree minimum is 1. If it starts here and ends here, it's got to cross the x-axis somehow. If it's an even degree, minimum is 0. Because I can't have it above the x-axis. When we talk about everything we talked about with quadratics last year, the same thing applies, except now we're taking it to third, fourth, and fifth degree. So we've already talked about 0 degree functions, first degree functions, linear functions, and quadratic or second degree functions. We're just going to take it to third, fourth, and fifth degree functions this year. Generally, the shape, the relation, or the similarities to everything else. What we've been talking about with constants, linears, and quadratics, they are a subcategory of polynomial functions. Okay, so a polynomial function is anything can be written in this form here. So some number times x to the power of some number, plus a second number times x to the power of 1 less than that number, to a third number times x to the power of 1 2 less than the original number, and so forth. There are restrictions for those numbers a and n. Okay? A must be a real number. Okay? So, real numbers. For us, just about anything other than negative square root 2 and 4 plus I. We're not. So basically, we can't have square roots of negative numbers or fourth roots of negative numbers for us. I can have fractions, I can have decimals, I can have integers, whole numbers, 0. I can have all those. Just the square root of a negative number doesn't work for us. X, the number n must be a whole number. So that means no fractions, no decimals, no negative numbers. We are only talking about positive whole integers and 0. Okay, so that's what it has to be. So this is a polynomial. This is not a polynomial because my exponent is not a positive whole number or 0. Sorry, positive integer or 0. Can't have fractions up there. I can't write this. That's not, I can't write that in this form with whole numbers because my exponent on this guy would be x to the negative 1. So this guy is not. This guy is not. There are a bunch of different ways of asking all of these. Sometimes they get a little tricky, as in one of the ones here. Is g of x a polynomial function? Well, if you think about this, x to the 1/2 minus 5. So the other way of writing the square root of x is raise it to the power of 1/2. Well, this is not a polynomial because it has a fractional exponent. So no, this is not a polynomial. This guy over here is. I don't care what order I write my polynomials in, although it does give me a little bit of fits, because I happen to like writing things from highest degree to lowest degree. But we have all of our integers, or all of our exponents are whole numbers. That's a 1. We don't write that, but that's x to the power of 0. So all of our exponents are whole numbers. The same thing over here. This one is, yes, it is a polynomial. because I can write this as 0x cubed plus 0x squared plus 0x plus 0. But I don't, right? But you can have your coefficients in front of your terms as 0. This one is not a polynomial. It is a polynomial on top, a polynomial on bottom. But there's no way that I can write that in this form like this. Okay, I'm going to get a fraction. So this one is no. This one over here is no, because it's an absolute value function. It's not the same. Why is k of x not a polynomial? This exponent over here, okay, that's a whole number, or that's a whole number, that's a whole number. Now we're into integers. So, no. Now here's the trick question. This one is a polynomial. In that I can write this as x minus 2. Because I've got the square root and the inverse function, the square. So the square root of something squared. Yes, so I can write this as a polynomial. This is. Now, here is a summary of zero degree functions all the way up to quintic functions. They have the general shape. The number of turning points will change depending upon what the function is. But if I say a quintic function, you know a quintic function with a positive leading coefficient starts down there, ends up there. Starts in 3, ends in 1. Same thing if I say a positive third degree function, third degree function with a positive leading coefficient starts down there, ends up there. A fourth degree function with a negative leading coefficient starts down in third, ends down in 4. Because it's very similar to a quadratic in that manner. So we are going to do some matching. We have, and I believe they're all upside right. Are your graphs the same as my graphs? Because I had these upside down at one point. Yes. Okay, so let's look at this. We've got 3 fourth degree functions. We have 2 third degree functions. That's a third, that's a third. And then we have a 5th degree. Let's talk about the odd one out. Which of these ones do you think is a 5th degree function? Aaron? Why do you say C is a 5th degree function? As it crosses the x-axis 5 times. Good. Now it does start up here and end down here. And we can see that matches because we have a negative leading coefficient. Starts up here, ends down here. That's negative in first, third, 5th, 7th, 9th, etc. Okay. Now, let's talk about third degree functions. What are left at our third degree function? Well, a third degree function is either going to start down there and end up here, or like this. So we have this one here is a third, and as is this one is a third. Now, how do we tell them apart? Well, looking up here, we have positive leading coefficients. Doesn't really help us because that means they both start down there and end up there. What's the other piece of information that we can get off of the graph that will, or sorry, off of the equation that will help me with my graph. Yes? Y-intercept. We have a y-intercept of 3 and a y-intercept of 24. Well, this looks like a 3 to me. I can't read my board. So, and this does look like a 24 to me. So this one here is f of x, because it's a third degree with a y-intercept of 3. This is, what do I call it? Q of x, because it's a third degree function with a y-intercept of 24. That leaves us our fourth degree functions. Looking at our fourth degree functions, black, we have a negative leading coefficient, a positive leading coefficient, and a positive leading coefficient. So I'm going to look at a fourth degree function that starts in third, ends in fourth. That's B here. The other ones start in 2, end in 1, and starts in 2, ends in 1. So now we are going to, again, our y-intercept. How do we distinguish between the two that we don't have? Well, we've got a 36 constant term, and we have a negative 12 constant term. Well, this is the only negative. So this guy here is going to be P of x. And then by default, this guy would be R. So there are 3 ways. Well, first of all, you distinguish by degree and shape. And as Taryn says, oh, this has got 5, so it has to be at least 5. It doesn't have to be 5, but we'll say it has to be at least 5. Then we go to leading coefficient, pointing up or down. Sorry. What's the end behavior? Yes, I do a lot of arm dancing in this one. Starts in 3, ends in 1. That has to be an odd degree function. Starts in 2, ends in 1, has to be an even degree. I can flip those around with negative leading coefficients. So my negative leading or my positive negative leading coefficients tell me some things, and then the other thing is my y-intercepts. That's if we give it to you in general form. Without technology, here we have a function. We should be able to get the maximum number of what x-intercepts from this, the maximum number of turning points. I'm really talking about turning points, but I'll explain here. The y-intercept and the end behavior. How does it end? So again, my arm dancing. Well, what degree function is this? Sorry? Okay. The degree is 3, even though I tucked it away down here. The degree is 3 with a negative leading coefficient. So that allows us to do, once we have that, now we can do our end behaviors. It's going to start up here in 3, or 2, I should say, and end down in 1. Because it's a third degree, so it's going to look like this. Oh no, it's a negative, it's going to look like that. The y-intercept. Rory, what's the y-intercept in this case? 1. I personally like to write it as 0, 1, but yeah, the y-intercept is equal to 1, crosses the y-axis at 1, because we have a constant value of 1. It's a third degree function. It can cross the x-intercepts a maximum of 3 times. It can cross it once, it can cross it or touch it twice, or it can cross it 3 times. Can't cross it 4 times. Now, turning points. This is where the graph changes the direction. So we know it starts up here crosses once, got to turn around, cross again, got to turn around, cross again. So that is the maximum number of turning points is 2. The maximum number of turning points is always 1 less than the degree. Now, a second degree function has to have 1 turning point. A third degree function doesn't have to have 1. Here's an example of a third degree function without a turning point. It has to have 3, or it has either 3 it has 2 turning points or no turning point. It can't have 1 turning point for a third degree function. I'm going to just go to homework here. So you have some whiteboard work on your textbook, page 114. And then attached to this, you have 6 questions, relatively simple. Just do 1 through 5 once you get to the homework.